Welcome back. In this lecture, we'll discuss independent samples t-tests. We'll begin by introducing independent samples t-tests and walking you through how to calculate them. We'll next talk about how to calculate effect size in the context of independent samples t-tests, and we'll close things out by discussing type 1 and type 2 error in more detail. Let's begin with some review. Both the z-test and the one-sample t-test answer the same question. Is the sample mean that we collected from the null population, or is it extreme enough that it's more likely that it came from an alternative population? This is possible because we know what the distribution of sample means should look like if the null is true. Specifically, it should be normally distributed with a mean equal to mu, the population mean, and a standard deviation given by the standard error. Because we know what the distribution looks like, we can calculate the probability of a given sample mean occurring if the null is true, in other words, occurring due to chance alone. And if this probability is sufficiently small, specifically if it's less than the alpha level that we've chosen, we conclude that the sample most likely did not come from the null population, and therefore we reject the null hypothesis. Importantly, both the z-test and the one-sample t-test require that we know the population mean mu. And of course, we don't always have access to this. Imagine a situation in which we only have two samples. So suppose we want to study whether knowing that you have social support available decreases anxiety levels. In this case, we don't know the population mean mu or the population standard deviation, sigma, for anxiety. All we have are one group of people that say they have social support and another group of people that say they do not have social support. The solution is to use an independent samples t-test, which tests whether the difference between the means of two samples is more extreme than the average difference between the means of two samples drawn from the same null population. Now, let's briefly review and talk about null hypothesis significance testing, NHST, for one-sample tests, the z-test and the one-sample t-test. The blue bell curve here represents the distribution of test statistics, either z or t, if the null is true. In other words, it is the sampling distribution of means based on samples taken from the null population. And importantly, because z and t are standardized, we know that the mean of this distribution is 0, represented by the teal line here. If we're just drawing samples at random from the null population, the average z-score, or the average t-score, of those samples will be 0. And as I mentioned before, because we know the precise shape of this sampling distribution, we can figure out what proportion of it corresponds to any given alpha level. In other words, if we select an alpha level of 0.05, we can define precisely which proportion of this distribution falls within that 5%. And we can define the precise critical value, either z or t, that defines the boundary between our critical region and the rest of the distribution. Then, once we've calculated our test statistic, in other words, the standardized difference between the observed mean and the expected mean if the null was true, we can simply compare our test statistic to the critical value. If the test statistic exceeds the critical value, we know that the sample mean that we got must fall somewhere within our critical region, here the shaded red region, meaning that it would be extremely unlikely to occur by chance alone. In other words, it would be unlikely to occur if the null hypothesis were true. Additionally, because our test statistic is greater than the critical value, we know that our p-value, the probability that we would observe an effect as or more extreme than the test statistic we actually did observe if the null was true, must be less than 0.05. We don't know its exact value, but because it's beyond our critical value and it's within the critical region defined by alpha, which in this case is 0.05, we know for certain the p-value must be something less than 0.05. And, as we've discussed before, remember that we can make a decision about whether to reject or fail to reject the null either by comparing the test statistic to the critical value, as we've done here, or by comparing a precise p-value to an alpha level. Either one works, and crucially, they will always lead us to the same conclusion. Generally speaking, when we are doing hand calculations of the sort that we're doing here, it's usually easiest to compare a test statistic to a critical value. On the other hand, if you're running these analyses using software, for example, using R, you'll generally calculate a specific p-value associated with the test statistic and simply compare that p-value to your alpha level. So again, this has been a recap of the logic of null hypothesis significance testing for one-sample tests, both z-tests and one-sample t-tests. The underlying idea is that we want to figure out how likely our test statistic would be to occur if the null hypothesis were true. If the test statistic is extremely unlikely to occur if the null hypothesis were true, we conclude that the null hypothesis is not true, and we reject the null. Now let's talk about null hypothesis significance testing for independent samples, t-tests. So here, this blue curve once again represents the distribution of test statistics if the null is true. Here, however, this is the sampling distribution of mean differences based on samples taken from a null population. So in other words, if we have the null population, we draw two samples from it, compute the mean of each sample, compute the difference between those two means, and plot it. We then draw out two new samples, calculate the means of each of those, calculate the difference between those means, plot it, draw out two new samples, calculate the means, calculate the difference between the means, plot it, and so on and so forth. And what we will end up with is a distribution that looks like this. Crucially, the mean of this distribution is 0. So, just like for the z-test and the one-sample t-test, because we know what the distribution of test statistics should look like if the null is true, we can figure out a region of the distribution that corresponds to any given alpha level. So, if we have an alpha of 0.05, we can figure out the region of the distribution that corresponds to that alpha level, in other words, 5%. And we can identify a specific critical t-value that represents the boundary between that critical region and the rest of our distribution. Then, we can calculate our test statistic. Our test statistic is the standardized difference between the observed mean difference, in other words, the difference between our two sample means that we actually observed, and the expected mean difference if the null is true, which, as we saw, is 0. Just like for a one-sample test, if our test statistic exceeds our critical value, we conclude that it would be very unlikely for us to see an effect that extreme if the null were true, and thus we conclude that the null is not true, and we reject the null. The key idea here is that even though the details have changed a little bit, we're now talking about the means between two samples rather than the mean between one sample and a hypothesized population mean. The underlying logic of null hypothesis significance testing is still the same. We can construct a model of what the distribution of test statistics should look like if the null is true. Based on that model, we can figure out how likely any given test statistic is to occur if the null is true, and if that probability is sufficiently small, sufficiently in this case meaning less than alpha, we conclude that the test statistic would be unlikely to occur if the null is true, and therefore we conclude that the null is not true. Now, let's walk through an example of an independent samples t-test using null hypothesis significance testing. Our research question is, does having social support decrease anxiety? Previous research suggests that simply knowing that you have people you can seek help from has health benefits. This can include friends, family, coworkers, CAPs here on campus, you name it. So, given that previous research suggests that knowing that you have social support has health benefits, we might ask, could it also influence anxiety? So let's say we conduct a study in which we have one sample of participants who say that they know that they have social support. We have a second sample of participants who say that they're not sure if they have social support. Both of the samples are the same size, each one has 60 participants. So now that we have our research question, let's move ahead with step 1. We'll set our null and our alternative hypotheses. We'll begin with our alternative hypothesis, that people who know they have social support will not have the same levels of anxiety as people who aren't sure if they have social support. We can express this formally as H1 is that mu1 does not equal mu2. In other words, our alternative hypothesis is that the population mean for the first sample and the population mean for the second sample are different. As always, Once we've defined our alternative hypothesis, the null hypothesis has to cover everything else. So in this case, our null hypothesis would be that people who know they have social support will have the same levels of anxiety as people who don't know if they have social support. And we can express this formally as H0 mu1 equals mu2. In other words, the population mean for the first sample and for the second sample are exactly the same. Another way we can think about these hypotheses is that our null hypothesis is that both of our samples were actually drawn from the same population. Our alternative hypothesis is that our samples were drawn from two different populations with two different means. Now that we have our hypotheses, as we see in the little blue box here at the top, we'll go ahead and choose our alpha and our critical value. Let's go with an alpha of 0.05, two-tailed. Easy enough. So now that we have our alpha, we need to figure out the corresponding critical t-value. Conveniently, the table of critical t-values that we use for the independent samples t-test is the same as the one we used for the one-sample t-tests. However, the degrees of freedom are different. For an independent samples t-test, degrees of freedom is equal to n-2, where n is the size of both samples added together. We subtract 2 because there are now two sample means in this calculation. So, if our sample size is 60 in sample 1 and 60 in sample 2, our n will be 120, which means our degrees of freedom will be 120 minus 2, which is 108. Take a minute to pull up the table of critical t-values listed on GauchoSpace and figure out what our critical value is going to be for degrees of freedom 118, alpha of 0.05, two-tailed. And the answer is going to be plus or minus 1.984. As a reminder from the last lecture, if the precise degrees of freedom you've calculated isn't listed in the table of critical t-values, always underestimate. In other words, go with the next lowest degrees of freedom that is listed in the table. Now that we have our critical value, we can calculate the test statistic. So here we see our equation for an independent samples t-test. Let's talk a little bit about the different components of this equation. In the numerator, the top of the fraction, we have the difference between sample means, m1 minus m2, minus the difference between the population means, mu1 minus mu2. In the denominator, the bottom of the fraction, we have the average difference, or variability, expected between two sample means from the same null population. In other words, the standard error. Our estimate of this variability for samples with equal sample sizes is given by the equation here. However, if our samples are of unequal size, we'll need to use a different equation for something known as pooled variance. Let's talk about pooled variance in more detail. And again, you can see the equation for this in the upper right. Larger samples tend to be more variable than smaller samples, which means that larger samples are a better representation of the variability of the population, which again is the thing that we're trying to estimate using the sample variability. This means that we want to give them more weight in the variability calculation, and we do this by multiplying them by their larger sample size. So if you look at the equation, you can see that in the numerator, we multiply n1, sample size for sample 1, minus 1, times the variance for sample 1, and add that to the size of sample 2, minus 1, times the variance of sample 2. We then divide this by the degrees of freedom, n minus 1 plus n minus 2 minus 1, which simplifies to n1 plus n2 minus 2. The resulting statistic, s squared sub p, is known as the pooled variance. This is the average variability of the two samples, with greater weight given to the larger sample. Once we've calculated pooled variance, we simply plug that value into the formula for standard error. So here, we divide the pooled variance by the sample size for sample 1, and add that to the pooled variance divided by the sample size for sample 2, and take the square root of the resulting sum. So, going back to our example, let's say that sample 1, which, remember, is our participants who know that they have social support, have an average score of 3.01 on a 1 to 10 scale measuring anxiety. They have a standard deviation of 1.35, which means they have a variance of 1.82, and as we established before, a sample size of 60. Sample 2 is participants who do not know whether or not they have social support. Let's say they have a mean score of 7.08 on the same 0 to 10 scale, the same 1 to 10 scale measured anxiety, that they have a standard deviation of 2.75 and a variance of 7.56, and they again have a sample size of 60. We'll begin by calculating the standard error. So, to find our standard error, we divide the variance of sample 1 by the sample size for sample 1, so that's 1.82 divided by 60, and add that to the variance of sample 2 divided by the sample size of sample 2, which gives us 7.56 over 60. We then take the square root of that entire amount, which will give us 0.4. Note that we're able to use this formula alone because both of our samples have the same sample size. If our samples were different sizes, we would need to calculate pooled variance first. Let's go ahead and calculate pooled variance anyways, just for a little bit of practice. So again, using the formula that we were given, we simply plug in our sample sizes as appropriate for n sub 1 and n sub 2, and plug in our sample variances as appropriate for s squared sub 1 and s squared sub 2. I won't walk through all of the arithmetic on this one, but our final answer ends up being 4.69. And we can check our work by plugging this back into our formula for standard error. You'll find that we end up with a standard error of 0.4, which is exactly what we found before. So, just to reiterate, if your samples are of the same size, you do not need to calculate pooled variance. You can just use the formula for standard error. If you choose to calculate pooled variance, it should give you the exact same result when plugged into the formula for standard error. So now that we have our standard error, we can calculate the test statistic itself. So looking at the numerator of the test statistic, we can ask, what does mu1 minus mu2 represent? And the answer is that this represents the difference between the means of the two populations that the samples came from. Now, conveniently, our null hypothesis states that mu1 equals mu2, and if this is the case, then mu1 minus mu2 must equal 0. So in other words, we want to see if the difference between our sample means, m1 minus m2, is different enough from 0 to be considered noteworthy. So let's go ahead and calculate. We can plug in our sample means for sample 1 and sample 2 into that first set of parentheses, 3.01 minus 7.08. Notice that the second set of parentheses in the numerator, mu1 minus mu2, simplifies to 0, so we can effectively ignore it. And then we divide that entire thing by our standard error, which we found to be 0.4. We end up with a t-value of negative 10.18. Now, you might wonder, what is the significance of the fact that we found a negative t-score? Well, suppose that we switched around the order of the samples. After all, calling one sample 1 and the other sample 2 was kind of arbitrary. If we switch the order of the samples, instead of subtracting 7.08 from 3.01, we would subtract 3.01 from 7.08. We would get the same absolute value. It would just have a positive sign rather than a negative sign, and we would get a t-value of positive 10.18. But, as I mentioned, the absolute value of the t-score would be the same. And crucially, the order of the samples will not affect our conclusion about whether to reject or fail to reject the null. It's either significant or it's not, regardless of whether it ends up being positive or negative. There's a StatsClass video that I've posted that covers the independent samples t-test calculation in more detail. I strongly encourage you to watch this to get a little bit more practice. One last thing I want to note here. Looking at the equation for the independent samples t-test, we can think of the numerator conceptually as representing systematic variability. In other words, variability due to the nature of the two groups. The denominator, then, represents unsystematic variability. In other words, variability due to everything else in the universe. And so, as we discussed in week 1, we're effectively testing whether there is substantially more systematic than unsystematic variability in our sample. In other words, if the ratio that we observe here of systematic to unsystematic variability is substantially greater than we would expect due to chance. So now that we've calculated our t-statistic of negative 10.18, it's time to make a decision. Notice that our test statistic, negative 10.18, exceeds our critical value of negative 1.984. Now, you may ask, why are we comparing it to negative 1.984 and not positive 1.984? The answer is that when we run a two-tailed test, we have two critical values, one positive, one negative, with the same absolute value. So we reject the null either when the positive test statistic is more positive, higher, than the positive critical value, or when a negative test statistic is more negative, is lower than the negative critical value. In this case, we reject the null because our test statistic exceeds the critical value. And we would conclude that people who do not know if they have social support experience significantly different levels of anxiety compared to people who do know that they have social support. So, as we discussed in the last lecture, in addition to calculating whether or not a difference is statistically significant, we can also measure the effect size. The effect size measure for independent samples t-tests is conveniently the same as we used for one-sample t-tests, Cohen's d. Cohen's d measures the mean difference between two sample means in terms of pooled standard deviation units. So here we see the equation for Cohen's d. In the numerator, we have the mean difference, m1 minus m2, and in the denominator, we have the root of the pooled variance. So if we want to calculate effect size, it's worth our while to go ahead and calculate pooled variance right off the bat. So here, our effect size calculation would be that d is equal to 3.01 minus 7.08 divided by the square root of 4.69, which, if you'll recall, is the pooled variance that we found earlier. Taking the square root of variance, of course, gives us standard deviation. So this will give us a d value of negative 1.88. So we interpret Cohen's d in the same way for an independent samples t-test as we did for a one samples t-test. D values of about 0.2 are considered small, D values of about 0.5 are considered medium, and D values of about 0.8 are considered large. And notice that here that we're talking about the absolute value of Cohen's d. So just in the same way that the t-statistic can be either negative or positive depending on what we subtracted from what, Cohen's d will be positive or negative depending on which group we subtracted from which. A good rule of thumb is that the sign of Cohen's d should always match the sign of your t-value, which is the case here. We got a negative t-value and a negative Cohen's d. Crucially, the interpretation is the same either way. So a d of positive 0.5 is considered a medium effect. A d of negative 0.5 is also a medium effect, just in the opposite direction. So here, as you can see, our effect size is very large, which suggests, in relationship to our research question, that knowing that you have social support has a very big impact on your levels of anxiety. I want to take a moment to discuss a particular corner case that a lot of students find confusing. I want you to know that it is possible to fail to reject the null, but have a large effect size. This often occurs because the sample size is insufficient to rule out unsystematic variability. So in other words, even though the effect is big, it's not big enough to reject the null given our sample size. Remember that sample size is an estimate of the true effect size. So even if you find a large Cohen's d, if the overall test is not significant, that suggests that may have just been a fluke. It was large, but not larger than what we would expect due to chance alone. Now, if this occurs, it is possible that if we reran the same analysis with a larger sample size, we might be able to actually reject the null. However, it is very important to note there are a couple conclusions we cannot make without more evidence. First, we cannot say that with a larger sample size, the effect would have been significant. It may be, but it doesn't have to be. Similarly, we cannot say that small sample size was the only reason we failed to reject the null. It may have been a reason, but there may have been other reasons as well. Now, as an analogy for why this is the case, imagine that you lose your watch, and you think you lost it on the beach. So you spend an hour poking around in the sand, and you don't find it. It would be incorrect to say, if I'd spent another hour, I would have found it. Because, of course, your watch may not have been at the beach at all, in which case no amount of searching would have led to you finding it. By the same token, it would also be incorrect for you to say, I didn't poke around enough, and that's why I didn't find it. That might be why you didn't find it, but it's also possible that your watch was never at the beach, in which case that's the reason why you didn't find it. So let's talk about reporting the results of independent samples t-tests. Much like when we report one-sample t-tests, there's a handful of specific pieces of information that we need to present in specific ways. Once you get used to this, the whole approach is fairly formulaic and is easy to tailor to the specifics of the situation and the research question that you're describing. I'll go ahead and walk through each of the elements of this results section in detail. So we begin by stating the type of test that we conducted, an independent samples t-test, stating the number of tails, and specifying the alpha level that we used. We next give a brief description of our research question and our hypothesis. We explain why we ran the test at all. We give a brief statement of the results in terms of the independent and the dependent variable. So here we say a significant effect of social support, our independent variable, on anxiety, our dependent variable. Next, we report the results of the t-test itself, this bit in purple. We begin by reporting the degrees of freedom inside the parentheses that follow the italicized t. We report the test statistic following an equal sign. And finally, we report our p-value. Again, recall that here, because we calculated our critical value, we do not have a precise p-value, but because our test statistic exceeded our critical value, we know that our p-value must be less than our alpha of 0.05. We follow this report of the test statistics with a verbal description of what happened. So here, participants who reported knowing that they had social support significantly differed in anxiety scores from participants who reported not knowing if they had social support. In that verbal description, we include both the mean and standard deviation of sample 1, in parentheses, and the mean and standard deviation of sample 2, also in parentheses. We report the effect size along with a verbal description, so the effect size was large, d equals negative 1.85, and we conclude with a description of the results that ties them back into our research question. So, individuals who knew that they had social support showed substantially decreased anxiety compared to individuals who did not know if they had social support. So, to recap, I'd like to show you a graphical representation of the testing process that we just did. As always, this blue bell curve here represents the distribution of test statistics that we expect if the null is true. In other words, the distribution of standardized differences between sample means if both samples are drawn from the null population. This distribution has a mean of 0, because if the samples are being drawn from the null population, the means should on average be the same, and thus the average mean difference should be 0. Because we know the details of this distribution, we can define the regions of the distribution that correspond to any given alpha level. And importantly, because here we ran a two-tailed test, our alpha of 0.05 must be split between the upper and lower end of the distribution. So notice that each of the shaded red regions corresponds to half of our alpha value, or 0.025. So in other words, 2.5% of the distribution is contained in the red region at the upper end of the distribution, and the other 2.5% of the critical region is contained at the lower end of the distribution. From there, we can identify the critical values that define the boundaries of those critical regions. So we know that a t-value of 1.984 is the lower bound of the upper critical region, and a critical t-value of negative 1.984 is the upper bound of the lower critical region. Our test statistic, the standardized difference between sample means that we observed, was negative 10.18. This substantially exceeded the critical value for the lower end of the distribution, and thus we can conclude that this test statistic would be extremely unlikely to occur due to chance alone. In other words, if the null were true. And because it exceeds our critical t-value, we know that the p-value, in other words, the probability of observing a test statistic equal to or greater than the one we actually did if the null hypothesis were true, must be less than our alpha level. It must be less than 0.05. If we were able to directly calculate our p-value, we could also reject the null hypothesis by observing that our p-value is less than our alpha. So let's talk a little bit more about p-values. So what I did here was created two samples with the same means and standard deviations as we used in our example earlier, and ran an independent samples t-test in R, producing output that looked like this. We get roughly the same t-test statistic. Notice that R automatically applies a correction for differences in variance between groups. This is what it means by Welch two-sample t-test. You'll notice it applies this correction to the degrees of freedom, which is why we have a fractional degrees of freedom, something that would not normally happen. The p-value that we've calculated here is extremely small. It's in scientific notation, but it works out to be essentially zero. This means, once again, that the t-value we calculated, negative 10.317 in this case, would be extremely unlikely to occur by chance alone if the null hypothesis were true. One last sort of stylistic note I'll make here is that you must never report a p-value of 0. Even if it is extremely small and almost 0, you would report that as p less than 0.001. So, let's talk a little bit more about our risk of type 1 and type 2 error. In this instance, which type of error did we run the risk of committing? Well, remember that we rejected the null, which means the only error we could have committed is a type 1 error. In other words, rejecting the null when we actually should not have rejected the null. So, is there a chance that we actually committed a type 1 error? Absolutely, there always is. But we used a two-tailed test, we used the standard alpha, and we had a pretty large sample. Which means we've done basically everything that we can to avoid making a type 1 error. In other words, to avoid wrongly concluding that an effect was real when it actually was not. Additionally, our test has decent power due to sample size. In other words, there's less of a risk of a type 2 error. I'll close this lecture by running over a brief recap of the material we covered. A one-sample t-test, like a z-test, requires that we know the population mean, mu. Unfortunately, we often have no way of knowing this value. One solution is to draw two samples, calculate the mean and the standard deviation of each, and then ask, how great is the difference between the sample means, the systematic variability, relative to the variability or difference within each sample, the unsystematic variability? Our t-statistic gives us a standardized measure of the difference between means because it divides the mean difference by standard error. We know how t-statistics should be distributed if the null is true. In other words, if both samples actually came from the same population. Which means that if t is sufficiently extreme, is sufficiently unlikely, in other words, is sufficiently unlikely to have occurred if the null was true, we reject the null.